Yo, yo, yo. What's up? What's up? Welcome back. Today we're working on my x86 operating system, written in Rust. It doesn't do a lot right now, but we're starting to get somewhere a little more interesting. There's no user space for this operating system yet, so everything's done in the kernel. Sorry. And what currently does is it boots. It has memory allocation, so we can use like hash maps and vectors and stuff. We get off like the goodies in the Rust standard library. It has async await, which is pretty sick. It means that we can do things like in parallel without needing actual parallelism right now because we don't have any scheduling or anything or multi-core, but we do get like the benefits of being able to do multiple things at once. We have logging to the serial console and VGA. So serial is like the like port on the back of your PC that like, or probably not on PCs anymore actually, but it's like 2-wire protocol. And what's nice about this is it's like when you boot in QEMU, this is piped to the standard input output of your virtual machine, which is pretty sick. So you can like copy paste out of there. You get like scroll back for free and shit. You have VGA. So I can like log all the same things to like this window that pops up that would correlate with my monitor if I was running on real hardware. And I have just like general logging infrastructure set up. I have unit testing infrastructure with QEMU, the support for the clock, or a clock, the slow one, the slow shitty one, but that also supports like date time. And I've started working on like PCI, and through PCI Ethernet, and through Ethernet UDP receive works as of yesterday. So if I like pop up in a little demo, we see like we have a vector, we have a map. So these like are proving like allocation is working correctly. There's like a date time, and we modify the date time and we set it back an hour, I believe. So we go from hours 21 to hours 20 on September 30th, 2023, which is today. We can like retrieve the MAC address from the network card, and then we'll run like an echo server for the UDP parser. So if I like cargo run and go down here and go like test hi Mick, we see like some stuff come back. All right, so we're chilling there. And so what I would like to explore today is how we can get data out. Right now we've got like parsers for UDP, but we don't have any like UDP generation, and there's a lot of stuff in these like IPv4 headers and UDP headers that are probably skipped, as well as like IP address resolution isn't handled right now. So I kind of wanted to like poke through all of that and figure out how that works. I imagine that it's going to be quite straightforward since we've already implemented a bunch of this, like we've already done the receiver side, and so we can probably like receiver to sender is probably not that hard. We just might have to fill in some fields that we didn't have filled in before. So that's what I want to do, and let's kind of jump into it. So this happened, we finished introing around like 3:17. Okay, so what's next? We want to set up a guest. So we're here right now. Set up guest to host UDP forwarding. So what we're doing right now is we're using QEMU in what they call like user mode, which I think is slurp. I think is what they call it, like yummy slurp juice from Futurama. Let's see. User mode networking is called slurp, and which I think is software emulates something. It basically, I think, it's doing like, it's acting as a router and doing like very specific port forwards internally. So what happens is I boot up QEMU and it opens up a listener, a UDP listener right now on port 6001. And when I send to that port, it gets routed into the virtual machine at a specific address. And actually what's kind of fun is we can look at what this looks like. So let's quickly run this again and say test, hello, hi, and we can, what QEMU will like dump the output of this. And so let's just see here. We can open it with Wireshark and we can see like, this is everything that happened in the network. So he's trying to send forward to 192.168.122.55, which is the IP of my VM. And we can see like, oh, here's the messages we sent. We see like a hello in there here. We say hi in there. Great. But we don't have anything set up right now for like guest to host forwarding. So presumably, I can set up something where I ask the I send to like a specific IP inside the VM, and that gets forwarded to some port that I've bound on my host machine. And we can use that as a proxy for doing some network testing. Now, obviously, this is like not as good as having like a full-on network, sorry, that we can like test with externally. But it's like a good starting point. So let's take a look at that. So I was doing some Googling before this, and it looks like if I look at like the QEMU man page, we're using the host forward option to do like UDP forwarding from like host to guest, easy. But the guest forwarding is like a little more complex. It doesn't have like UDP, it only has TCP, and so it's like, why the fuck not? And the quick Googling I did indicates that since UDP is so simple, you don't actually need something as complex. Like, it doesn't need to be built into the command. I think, if I understand correctly, what they do is you can set up like a character device, which I think is just like, here's a stream of bytes. And you, like, QEMU will like just take the output, like forward anything that you get into that character device, and then you read that to character device using UDP. So you could probably do something else where instead of going to a character device, you could like to a UDP port, you could actually do like standard output here, if I understand correctly. Right, so let's look at like the char dev. Right, like you can send it to a UDP port, but you could also send it to like the console or to a specific virtual terminal or like outside your own parallel port. There's like all sorts of shit you could do if you wanted. So it's just like a more flexible mechanism, I guess. But for now, we'll just like do UDP forwarding because that's simplest for us. Keeps things in sync, I think. And I think just copying this guy's command is pretty sane. So what he's doing is saying, I'm setting up a character device. It gets forwarded to a UDP port on localhost port 800. And here's like an ID for it. And then when we do guest forwarding, when somebody sends to 10.0.2.1 port 8000, we'll forward that to that character device. So let's try that. Okay. So here, this is just going to go boom, smack dab in the middle here. And let's change some of this. So I think the host here is optional. It will default to localhost or go to the man page. So if I look at man QEMU and look up cardev, yeah, cardev. One sec. UDP. Here, the host defaults to localhost, so there's nothing to change here. Port is required, sure. Local adder is anything, great. Local port is anything, I guess. So I don't actually understand why we need that. Thinking. It's okay. And then we will, yeah, sorry, brain fart. Yeah, so that's it. So we just sent a UDP port 8000. Or maybe we should do 6001 or something to match what we're doing on the other side. So I think what that means is we can like read that port. Actually, now that I'm thinking about this, I don't actually understand this very well. So this is a UDP port, but that means that we need somebody to like sniff the UDP port or something. At this configuration, any guest datagram sent to this is forwarded as a datagram to 127.001.800. Oh, okay, perfect. And then we have the guest forward stuff, and we're going to do the same thing where we have like 6000 is outgoing, 6001 is incoming. And there we go. So what we should be able to do here is we can have this as our outgoing, and we can have nc-u, so UDP netcat, and we can turn this into a listener on port 6000. And I believe what should happen now is if we get our UDP outgoing correct, we should see it show up here. So right, if we did this, we would like say stuff in here, we send UDP port packets, and they show up on the other side. So we should be able to see the same thing on the other side. So let's say that this is done but untested. Untested. And this is done at 10:22-ish. Okay, so now we have to figure out, like, how the hell do we get this IP, right? So from our Ethernet driver's perspective, when we send something, we don't send to an IP, we send to a MAC address by just like filling in a MAC address on the Ethernet header. And then it's goes onto the wire, and some, like, all network cards on the network kind of like will see that, and they will say like, oh, that's for me, I have that address, yum 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 yum. But they don't have IPs. The IP is more of like a software thing. And so what we have to do is we have to like send something to all, I think we send something to all network cards on LAN. And we say, like, I'm trying to send to this IP address. Who should I fucking talk to? And here's where I get a little hairy. I think that your router would say, hey, I'm good for, like, basically anyone. Like, hey, I can go over there. I know how to get there. I'll like go send it to this other router, and he'll send it on to that guy. And I've asked him who I should send to, and he said, me, right? And so I think that's how it works. But I'm also not sure it like matters, because we're not trying to get multiple hops right now. And we have like a sample of the network asking us where we are, right? He just kind of broadcasted out to like the world. He said, like, I want to talk to this IP 192.168.122.5.5. And he sent that to everyone, right? He's just like, hey, everybody, who has that? Brought by doing a broadcast. And then we respond. We go like, hey, that's me. So I think we could do the same thing here, where we know this is hard-coded right now, 10.021. This is where we want to talk to. And then we can use that in our ARP requests. So let's kind of see what that looks like. Okay. So what we have here is, let me look. Sorry. So we have our like demo thing here. What happens is our kernel initializes through this like kernel init, and then we run this kernel demo function down here. So we just say like, we pass in our kernel to this function, and we call the demo, and then we exit. But what we want to do is probably like add in some like writing as well as in here. So we can say like outgoing is async. Let's see. We call self.rtl 8139 write, and here we're gonna write out like our ARP request probably. This takes in like Ethernet packets. So we'll have like let packet equals generate ARP request, and for IP 10.8.0.1. This is going to generate like an Ethernet frame that we can just punch in here. So we'll say packet. And this is going to be a probably like a vector of U8, right? So we're probably going to like allocate some memory in this function and pipe it back out, because we don't know how big the ARP request is going to be. Theoretically, we could know because ARP requests are of a fixed size, but this is just kind of easier. And what's kind of nice about working in the kernel is the like memory allocation overhead is not nearly as high as it would be in user space, because we don't have to do like a kernel context switch. Now, there is overhead, but in reality, I also just don't give a fuck, right? Because this is a hobby OS running in a virtual machine with no goal at all, and everything that we do will be fast enough forever and ever. So I don't actually have to worry about this at all. But I'm just pointing it out that I'm not really worried about allocating for multiple reasons. So probably ARP packet generation belongs in the network module, And probably we want to stick it near all of the other ARP shit, which is out around here. And we actually have a generate ARP frame function already. But this doesn't generate an Ethernet frame. But we also already have Ethernet generation, because last time we had to respond to an ARP request with an ARP response, which is very, very, very similar. So maybe here we have generate ARP request, and this is for IP, which is a vec or a U8.4, and maybe like a reference to a U8.4. Right? We don't actually need a full U8, and maybe this should be a slice, maybe not. I don't know. I don't really give a shit. We'll figure that out later. And then we will let's see. So this is going to take in the IP, and we're going to do something very similar here. We're going to call generate ARP frame, and we're just going to start punching in our parameters and figure out what we're missing. So we're going to pass in ARP frame params, and what's it going to bitch about? It's saying that we're missing a lot of shit. Let's actually just go over here and we'll copy paste all of these. This is easier for me to think about. So we delete this and we delete this. Oopsies. There we go. So we have all this stuff to fill in. And what do we know off rip? We know operation is going to be a request. We know that the address length is going to be 4 and the hardware address is going to be 6. And we also know that the hardware type is going to be 1, I think. Let's double check our reference here. Hardware type is Ethernet 1. Protocol type is IPv4, which is this. And then our sender hardware address is us. So we actually have to pass that in. Right? Which is going to be this, MAC. We need to copy it. The sender protocol address is our static IP. So this is a generate IP for generate ARP request. Takes in a remote IP, not just any IP because we have multiple. Right, remote IP. But it also takes in like a local IP, our IP, which is a U8.4. And that's here, local IP. And then from our reference here, we can just fill in the MAC address with like, I don't know, zeros, because we don't know. So we can just say 0, 6. This will be an array of the 0, 6 times. Easy. Okay, so there's some stuff in here that we should obviously abstract. So this got, like, us having to like manually punch these in is kind of fucked. And we probably shouldn't need to do these. These should be like enums that are pulled in from somewhere. So we'll just say name hardware call type, maybe make default. Right? And we'll deal with that in a second. So now when I go back to main, I should be able to go back to this right call I was making, and I can say ARP frame is generate ARP request for this for the remote IP, giving me my local IP and my MAC address, which is self.rtl8139 get MAC. Okay. This is in the net module, so we just throw a net : on there. And here we need to borrow this because it's given as a reference. And now we have to say net generate Ethernet frame. And we just kind of do the same shit here, where we say we're going to pass in an Ethernet frame params. And here it's wants us to shove some stuff in here, so we'll just do that. So we do some vim macroing to pull out the shit we care about. Payload is going to be the ARP frame that we just used. The ether type is ARP, so I think I believe that this is already named. Let's just double check that. Ether type is just a hard-coded U16. So in reality, we should name that. So we can say enum ether type. We can represent this as U16. Then take an ether type here. Say ARP equals 0, I think it's 0806. It would be sick if I got this right. Absolutely sick. Ethernet frame Wikipedia. We can Google this to quickly check. Google it, Wikipedia it. And we have ARP as OX0806, which is what we wrote here. Boom. Good guess. And we don't really have any other types we support right now. We will eventually have to put in other ones, but we actually do. We don't send IPv4 yet. The only thing we send is IPv4. Cool. So now we can just say this is ether type as U16. UDP bytes. Easy peasy. Big bang boom. And that means that here we can say that we want to send ether type ARP. And this needs to come from net. So first we need to make sure that this is publicly exported. So we need to do that. And then we need to come here and we need to import it. So here we have the net imports and we just shove in like an ether type in here. There we go. Okay, source Mac, that's our Mac. So we already have that here. We can say let Mac equals self RTL8139 get Mac. And then here we pass in Mac by reference. Oh my gosh, it's not on a new line. Okay. So this is Mac. And here we also have Mac. And then the destination Mac is everyone. So we have a broadcast the world. Okay. He actually wants me to copy this guy, not pass him by reference. And then we can write the Ethernet frame. He needs to be passed in by reference or else somebody gets angry. And what is it complaining about? About borrow? Who doesn't like the borrow? Oops, so this should also be ether type ARP. And what is wrong with this borrow? Returns a value referencing data owned by the current function. And that's because we forgot to wait for this to complete. Okay. So now what we should be able to do is we should be able to do the same thing here, but sorry, hold on. Brain's melting. We should be able to just say like outgoing, oh wait, and maybe log of things as like info, writing ARP request, writing or waiting for outgoing message. Okay, very, very cool. So if we run this, we're close, but he doesn't like this, so let's go to net rs34. So this has to do with our, this has to do with this guy. What's he bitching about? Move occurs because this is type ether type, which does not implement copy. Oh my god, you're such a bitch. Whiny, whiny bitch. So here we just derive copy and clone because there's no expensive shit going on here. This is just a U16 that fits in a register. Copy's fine. We run this now. And here we sent our outgoing message. Which means that if we open in Wireshark, the first thing we see, is this broadcast. And it is a broadcast that says, who has 10801, tell 192.168.12255. That's me. Perfect. Perfect, perfect, perfect. So Now, what we should be able to do is we should be able to thinking, sorry. The question is, why do we not see a response sent from QEMU? I would expect QEMU to be like, me, I have 10801. So let's just double check some shit in here. So let's look at the QEMU command that we're running. And do we have 10.8. Oh, it's not, sorry, it's 10.0.2.1. That would explain why nobody answered. So let's go back here, and this is .10801. That's probably like some IP that I've used from using like OpenVPN. I think that's their default, and it's like hard-coded in my brain deep in there, and it will never leave. It's there forever. Which is annoying, but we'll live with it. And now, if I do this, we run it, no packets are received, but my network dump should now have me saying, who has 10.0.2.1, and there's still no fucking response. So I wonder why that would be the case. Thinking. Maybe we broadcast that too early before we're listening. No, because QEMU would still record that it sent that to the world. Let's just double check again our QEMU command. So now we are, in fact, for sure at 10.0.2.1, which is here. Oh, but maybe because we opened up a listener here, when we run QEMU, it tries to open that port and it fails and just continues because I completely forgot that was there. So let's try one more time, cargo run, and maybe we disable our like sleep here because it's fucking annoying waiting that long. So here we just don't do this. Easy. Let the cargo run again. And please tell me that we have something to look at. Nothing. So here's where I'm starting to get a little confused. I would think that because we are sending what seems to be a valid ARP request, right? We have all of these fields are getting parsed by Wireshark reasonably, and just nobody's answering. So I wonder if it's possible that broadcast packets aren't actually being broadcast. I was going to say that like maybe the RTL 8139 needs us to actually set some flag on there. But that doesn't make sense because he's just dumping packets on the network. But let's do some sanity checks here. So look at the OSDev wiki RTL 8139, and we'll find our documents. But I'm pretty damn sure that there's nothing to enable on this guy. Let's see. It'll be in the programmer's guide or the datasheet, and the datasheet would probably have it under like the transmission register setup. So somewhere in here, somewhere in this guy, we have like a global transmission configuration. This guy, TCR, at 040H. And does he have anything in here about like, oh, I'm not gonna do broadcast? Okay, an aside here. This is really interesting. So I spent a lot of time, a couple streams, like I think 2 streams ago, trying to understand how to CRC our Ethernet packets, because if we didn't do that, then we wouldn't be able to send valid Ethernet. But it actually turns out that the card would just fucking do it for us. So that's annoying and something to jot down for later. So we'll just put this here and say, whoops, we can ask the RTL 8139 to calculate the Ethernet CRC for us. And I don't see anything in here about like broadcast, which makes sense, right? Like we have a broadcast address in our Ethernet frame. So let's look at this guy again. So let's assume that this is okay for now. Locally administered address. This is not the factory default. Group access address multicast broadcast. Okay. And our source is an individual address, unicast, locally, sure. And this is a reasonable ARP request. So let's see why, let's look up, how do we look this up? QEMU guest forward ARP, maybe somebody will. QEMU doesn't ARP to the host, and my host is guest forward. What is this gonna say? Okay, blah, blah, blah. ARP table. In the process, I learned a lot about how ARP services work, blah, blah, blah. Long story, but now if I do a redirect on the command line sending for, what the fuck is this? Shut the fuck up. If I do a redirect on the command line sending, for example, 6,000 on the host and 5,000 on the guest, and do netcat, everything works great. I can get in from the host to the guest. Hey, this guy's like, he sounds like me. We're doing the same shit. And if I start up listening netcat on the host and get a proper guest forward on the command line, that works fine as well. If anyone interested, when my Linux starts up, it sends an unsolicited ARP associating 10025 with the correct MAC address. So that's probably his internal IP. Suppose at this point I try to do netcat 02.10.02.15. This connection is refused without ever hitting the net drivers. If I do blah this, it does search the ARP table for the 15 address and finds it. Obviously, QEMU sends back the ARP reply. And okay. So oh, dude, that's fucked. Dude, I'm so glad this random guy on the internet just happened to do the same thing as me, because I would never fucking guess this. That's so fucked. Oh, God. Okay. So that saved me a lot of time. So I bet if I now say I am, like, what did he say? He said 10.02.15. That should be the same subnet. If I run again, does QEMU now answer me? No. We were close though. So 10.02.1, 10.02.15. Okay. So maybe we can look at here. So netcat. So this guy should say localhost. Not that this matters yet, but this should be, I should be allowed to search there. And maybe we're not giving it enough time to respond anymore. So let's actually turn that sleep back on. Just a theory. Okay, so we open again. We go back to the network dump. Can I close this? Maybe we're not refreshing. So let's just do a quick double check here. And we still don't see the fucking response. Why? Why? How can we debug further? So let's see if QEMU can give us any clues. So this guy gave us a good idea to look at the slurp implementation. And is there anything in here about like ARP? Or is there anything in like this whole thing about ARP? Announce. Okay. So maybe he announces on boot or something. Let's see what this guy said on the internet again. He said, if I do this, it does search the ARP table. Find it. Then anyways, it just rejects everything not on the same subnet. It sends an unsolicited ARP associating 10.02. So this is like on the guest side. He's saying, I tell the world when I boot that this is my MAC address. But who is 10.022? So let's just do like another quick sanity check here. Maybe 10.081 is like a reserved IP. And that might explain why he's using 02 or whatever. So he's using 10.022. So let's just, again, just try to get a little sanity. So what's he saying? He's conflicting invalid host port. Hey, yo, what's up? 10.021. So why is that conflicting? host port and guest forwarding rule. So he wasn't okay with 10.02.2, but he was with 10.02.4. Maybe somebody else already had 10.02.2. Not sure. Drinking some coffee. How are you? We're doing good today. We're doing good. Okay, well, let's just for sanity's sake, we'll try not talking to 10.02.1. We'll try talking to 10.02.4, and we'll see if that does anything interesting. I don't expect this to fix anything. Warning, hub with no nicks. That's a good warning. And let's see, I bet nobody answers that. Yeah. So actually, let's go back to main, or what's it called? The QEMU command line. And let's go back to 10.02.1, which we think should be the router. And do we get that same warning? Yeah, warning hub with no nicks. Okay, so this is probably, we should read the output of our software, right? Because it'll tell us interesting shit. And I'm willing to bet that the QEMU internal network is just like, where are you going to go, bitch? Like, you're not connected to anyone. We can kind of confirm if this is related. We can try just like popping out some of these command lines. So let's back this command up. And let's turn off the guest forward stuff. Oh, I'm an idiot. Haha, okay. So I think that I tried to set up a host forward and guest forward rule. Like I set up like my guest forward rule pointing to no one. So here I should take this like command. This is wrong. This is what I get for blindly copy pasting from the internet without thinking or using my brain. And we should append this to our existing network device. So now our rules are, we have a network device, it's in QEMU user mode, got this ID, we're sending these host forwarding rules, and we also now have guest forwarding rules. Bing, bang, boom. If this doesn't fix it, well, it was worth a shot. Fuck. It was worth a shot. We are getting closer though. So we did remove that warning, which is good. Do I still have the car dev? I do. And I want to see Wireshark on KDE. Oh yeah, I think they actually have two versions. I think we have like Wireshark QT and Wireshark GTK. I think they've just abstracted it so they have like multiple UI backends. So yeah, I'd like KDE, QT, whatever, similar shit. Let's also change this 192 because we're now at 10.0.2.15, I think. So let's just make sure that we're still receiving packets. Great. And if we open up this guy, fuck. Wrong button. Yeah, so it's very odd to me that like we're QEMU's host, he's willing to say, yeah, I'm gonna broadcast this out, but the guest, if he does the same broadcast, doesn't get a response. Code still uses 10.0.2.4. Damn, you're quick, man. Are you sure? Oh, I see 10.0.2.1 here. 10.0.2.4. Yeah, no one's using that. As far as I can tell. 10.0.2.4. Why did that search succeed? Oh! That's because this is fucking unsaved. God fucking damn it. Good catch. Oh, this is... Okay, so we have like double log waiting for packet, which is really good. That means that we probably got the ARP response. Thank you. You're a genius. Oh. Mwah. Okay. Solid. So we now have this like MAC address that's associated with QEMU, and I'm pretty sure I've seen this 0A00201 before. It sucks that that's stuck in my head to the point that I recognize it, but I do recognize it, and so I'm pretty sure this is right. And so now what we have to do is we have to like, okay, think about it. We're gonna send something, and we're gonna get a response. And that response is going to come in our like read handler, which is like completely separate from our write handler. So what we actually have to do is we have to set up this like read and write in parallel, and they're going to have to access some shared ARP registry, right? Because if I want to send to this IP 10.0, what is it called? 10.0, come on, 21. I'll need to ask my ARP table, where the fuck are you? So let's look at that. So what that means is this outgoing thing, we don't actually want this to be like an async thing. We're going to want this to be somewhere where he's going to read this out, and he's going to be like, self ARP table, like, what is he going to say? He's going to say like, contains, he's going to like ask if the ARP table has this IP in it. So let's quickly just put that into a constant. So this is this guy. And he's going to be a U84, which I should eventually make a type for, because passing around these U84s is like anything that could be a U84. Is it an IP? Is it not? I don't know. But for now, we're just going to leave this for now. And we pass in remote IP here. And what we almost want to do is we want to be like, tell me when this is in the ARP table. We might want to do like self ARP table, like wait for remote IP. And that's going to be an async thing. And the question is that crazy? That could hang forever. But if it doesn't hang forever, we give up. Or no, we don't give up. We get the right. And if it does for some reason fail, like nobody answers us, what do we do? I guess we would just have to time out, right? Because there's no one telling us that they go this way. And I guess the way like the real internet handles this, just guessing, is like DHCP/DNS handles this probably. Like I'm just guessing, full on guessing. But am I like sending an ARP request to get to Google? No, I go to Google, which uses DNS to resolve an IP, and yeah, it could be ARP if once I get the IP. It could be something like a routing table provided by my router back through DHCP or something. I don't know. Full on guessing. I have no idea. But I was trying to think through that to think like, can I use like get by host name or something as a guess for like how I should handle this. I guess I could try like looking at the C documentation for what will happen if I try to open a socket with an IP that I can't route to and see what it does. So I think it's like man to socket. Or I guess man connect. Here we go. So here I provide an address, and presumably ehost unreach. Dude, this guy's ready to go. Ehost unreach. Ehost unreach. Is this real? Yeah, okay. So where does this come from? Obviously, if I Google anything related to this, we're just going to get a bunch of people being like, I saw the error ehost unreach. What does it mean? That's not what I want. I want to know how the fuck they send that. Is that on like connect or on create? I guess what we can do is let's just like spin up a little test Python thing. And I think it's sock dgram for UDP. Let's just quickly Python UDP socket. I think it's sock dgram. Yep, socket sock dgram, and then we send a message, and there's no connect in there. Okay, so let's just punch in like a garbage IP. So I think that we could do this. Was it inet? AF inet makes sense. Internet UDP, and we send a message. to some IP that hopefully doesn't exist. So we'll just say use like some internal IP, so like 192.168, and I think I have like nothing on .4. One, and I guess this should be in quotes probably, just a guess, and we'll send to port 80, and presumably this will error in some way. It doesn't like that this isn't a byte string. I think, can I just put a b in front of it in Python? Tuple cannot be interpreted as an integer. Oh, interesting. Because this is sent to 2. Okay. What happens? So actually, surprisingly, no error. Does it just go into the void? How do I validate this at all? I guess I just, in Linux, you only get a host on each of the route lookup fails. IRC ARP lookup failures will only be returned on the error message control oob side channel. Ooh, that's a lot of words that I've never seen before. So route lookup fails, that makes sense. And ARP lookup fails will only be returned on the error message control oob side channel. So that's I haven't seen before. So error message control. Let's do some quick Joule. Socket. No, we're not getting Google results. I'm sure that you're just maybe saying something sane, and me Googling those exact words is not reasonable. So I've seen what you're saying is that like somewhere I have a way to like ask someone if there was a mistake somewhere. But it makes sense. So you're essentially saying that I would talk to Linux. Linux doesn't know, and he just doesn't tell you. Which seems reasonable. Okay, well, I guess for now, I will just accept. I'm okay with this failing after some timeout. I think I'm okay with that. So, probably in here, what we would do is I would give myself like a little sleep. And I would say if I don't get a response in like a second, give up. Which means that I do something like this. And I would say like this is like ARP lookup. And here I would say I would like wait for one of ARP lookup or sleep future. I actually don't know how to like pull the answer out of this. So he returns back a select AB. And what is that? We have to look up the futures doc. One sec. So we have select. I know how to use, I've used like this macro before, but I couldn't get it working in std. This is like a kind of nice, you just do like a call this, and like if this thing comes back, I can do something with it. If this thing comes back, I can do something with it. What happens if I call this? He returns a select AB, and let's look at a quick example. It just says like, do I get left or right? Sure, that seems pretty reasonable. I've also seen like a select all, and now the question is, how would you work with that? Oh, it comes back as an iterator. And so you would like collect the results into a vector or something and see each option, each item was like would have a future in it. Huh, okay, I guess we'll get to that when we get to that. But I'm curious now what happens on the one that succeeded. Maybe they just give you like a future okay or something. Okay, back to this select. So we can just match on either left or right, easy peasy. And so we say here if the thing on the left succeeded, then we're good to keep going. And if the thing on the right succeeded, then we timed out. So we can look at like either and right. Or shit, wait. Is either left the thing that succeeded or the thing that failed? Future 2, future 1 is the pending one. Future 2 is the one that succeeds, which means that here, future 2 is the thing that succeeds, and value 2 is result from future 2. Value 1 is received value 1. Okay, yeah. And this represents future 2. I see. So the thing on the left is always the one, the first item in the tuple is always the one that succeeded, and the other ones are the ones that didn't. Which explains the vector thing too, actually. That means that in the vector one, you probably have like the first element is the one that succeeded and all of the other ones aren't finished yet. Or something. And you don't really worry about their order anymore. Maybe. I don't know. We'll see. So we have here, we have, if the right one is the thing that happened, we just give up. And we say, warning, maybe this is my first warn log ever. And we will say, ARP lookup for this IP failed. And this is remote IP. And if the thing on the left the ARP lookup works, we'll have the, I guess this will give us the MAC address. I don't know. I guess we'll make it up as we go. But for now, we'll say that'll give us the MAC address. And I guess we just return the MAC address here. So we say let MAC is equal to this whole thing. And we return here. We just bail out of this whole Shazam in this case. Now, this return, I actually don't know what happens when you return from an async block. It seems like this would exit the containing function because I don't think asyncs are returns, but then also like this isn't awaited in here. So maybe return in an async block is just invalid. That would be actually a completely reasonable answer. So let's just get everything compiling and see how that works. So we'll replace this with sleep, another sleep, just for sanity. He doesn't like the await here. Interesting. Why not? Oh, probably because this is probably like a garbage lint. I think that I've seen that when the features aren't pinned. Yeah, where pinning is just like your way of telling the Rust compiler that you're like confident that this won't move. Not confident. There's like some sort of like guarantee that it won't move. And you can just get around this. So what happens is like I've constructed this like future type and it's sitting there with the type future, but the future can like move around. I can copy paste that. Like I could return from the function and then it's like address will move. It'll like move from one address on the stack to another address, right? And the pin thing that is requesting, it basically gives this like guarantee that like I promise like this thing can't fucking move and I can't like use like a memory swap or a memory forget. I can't get rid of it. Oops, I'm not in the right docs. So I've like read these docs for this module like 40 times, and every time I read it, it's like it's complex and confusing, but we'll just like keep it in our head for now as like I promise it can't move. And all you have to do is say core pin pin, or if you're in like normal Rust, you would run std pin pin. And we'll just quickly pin these guys. So let sleep fut is the pin version. We'll just pin it, and we'll say let sleep fut 2 is the pin version of sleep fut 2. Boom. And now we're compiling. So I don't remember why I went through this whole ordeal, but we are compiling now and everyone's happy. So let's go back to this ARP lookup thing. So we'll say delete these. ARP lookup is this. We probably have to pin him too. So we just do this, core pin pin ARP lookup. And now we just have to start looking at like this ARP table thing. ARP table. And I guess we'll have like a little checkpoint here when we have like a MAC address that we can send to. So let's just kind of say in here, info resolved MAC address. And we'll print it here. And if we see that log, we'll be very happy. And if we don't see it, we'll be very upset. This shouldn't be ARP table, this should be ARP lookup. Very nice. Okay, so now let's start looking at like an implementation of an ARP table. So I guess here we need an ARP table in here, and we'll make it of type ARP table. We have to create a thing called an ARP table, which will be empty for now. And now he's complaining that we need a function to wait for, so we'll say impl ARP table, and we'll make an async function wait for, which presumably takes self by reference. Sure. Really, we're actually going to need interior mutability on both the read and the right side of the table, because this wait for, we like, if we're holding onto the ARP table on the right side, we'll also need to reference the ARP table on the read side, and interior mutability is just kind of easier to deal with that. Especially if you're in a state where you're like, this wait for actually has to like know that he should drop the mutex while he's waiting. Anyways, this guy returns a U86. And I guess we just assume that he always succeeds. This like mechanism of waiting, we're assuming that he will always succeed. And we're using like external control to just say, I fucking give up. Which is kind of nice. It means that we don't have to like handle, what do you call it? You don't have to handle like like error handling or anything from here. Let's just kind of initially, we'll just punch in the MAC address that we know is correct, just as a way to check that the code is working, and then we'll loop back for actually doing it. So this is 52, 55, then we have 0xO-A, 0xO-O, 0xO-2, 0xO-1. And is he unhappy? So he actually needs to take in the IP here, of course, which is a U84 for now. And there we go, we're chilling. And now in our kernel, we just have to construct the ARP table. So we'll say ARP table is just a new ARP table, really. ARP table is ARP table new. And I don't think there has to be anything fancy going on here. We just need a new function that generates an ARP table. And for now, he just returns some empty little guy like this. Okay, now we run, and we should see that log that says like, hey, we resolved a MAC address. Where is he? Resolve MAC address right here. Resolve MAC address. This is the guy. Perfect. So we know the scaffolding works, and we could continue on going this way if we wanted to. Now the question is do we want to keep going on the ARP table side first, or do we want to just plow forward, pretend we found the ARP response, and try to send a UDP packet? I think we get like a nice little like intermediate win if we go for the ARP stuff first. I think it's not very hard, and so I think I'm gonna go that way. And I guess we could argue that we would have higher, like de-risk wise, it makes sense to keep going because we have a guess of what we would want to do here, but we don't have a guess for what's coming next. But fuck it, I will just do the ARP table first. So in here, we're gonna have a hash map of IPs, which are U84, and I'm starting to type U84 enough times that like my internal gag reflex is starting to go. I'm starting to like feel like barfing because I'm writing such poor code. And instead, let's just make an IP address type that's a U84. Easy. And we can, we'll eventually have to create some like implementations for this, but for now, let's do this. And now we can write IP address everywhere, and that makes us happy. And actually, for like initial compatibility, that makes this easier. So we can actually just name it IP editor, and instead of trying to like strong type it like this, we can just make a type alias. And this is like worse, but it just means that interop between the code we've already written will be nicer, and I can strong type this later. Fix me. This should be IP address should be strong typed. And really, this isn't IP adder. This is IPv4 adder. But until IPv6 exists from the perspective of our operating system, we can just pretend that IPv4 is the only one that exists, right? We're just from like, when was IPv6 introduced? We'll just pretend, dude, 27 years ago, and we're still fucking up adoption? That's wild. I assumed it was at least after 2000. Okay, so we'll just pretend that our operating system is from before the year 1995, before this existed. So this goes to a MAC address, so we'll do the same thing where MAC address is a U86. And we'll just have a hash map that goes from IP address to MAC address, easy. And then what will happen, right? we need some mechanism in here to wait. So what we could do is we could like loop and sleep poll, but that sucks. Or we need like, what you would do in normal code here is you would use like a mutex and a condition variable. But we don't have that. Well, we do have like a vec dequeue that we can use as like a channel to post stuff on, but then the question becomes again, how do we like signal that it's time? And I guess we would need some sort of wake up handle, right? So internally we would have like the errors are going to bug me and I won't be able to think as strong. So let's just quickly get that out of the way, where we use hash brown hash map. I've been trying to avoid external dependencies, but I think hash brown is actually like a fair thing for me to steal, because the standard library of Rust uses hash brown under the hood, and I think using Rust standard library I think is fair. But we don't have standard library and there's no like core implementation, whatever. Okay, so this is also going to bug me. So we say let table is equal to hash map new. And we punch the table here. Bing, bang, boom. He's going to bitch that these guys don't implement hash, except they do. Great. Everyone's happy. Okay, so where was I? We need some sort of wake-up handle. So the first thing we're going to do, right, is we're going to have like a mutex in here. And by mutex, I don't actually mean mutex because we don't have any multi-threaded code. And if you used a normal mutex in these like async functions, it would be like fucked. But we do have, by fucked, I mean you would just like immediately deadlock, right? Because if you're locked, you wouldn't like ever bounce out of the future. Right, what happens is like Rust goes like, he looks at all of his features in his hands and he goes like, are you ready? Are you ready? Are you ready? And until they call await on something, they don't like exit. What happens is it like runs up a chunk of code up until an await and then bounces out. And with a regular mutex, if you deadlocked, you just would never bounce out. So what we did, we implemented like a mutex that handles that, and it's actually like quite straightforward. All it does is he looks at like a count of how many people have access to him, and if the count is 0, he's good. And if the count is not 0, he just makes a feature that checks if it's 0. So here he just says like, if the count is 0, then I'm free, and when you pull me, I'll check if the count is 0 again. So we have this async mutex. So let's wrap the hash map in that. And we need to use this. So I think we have create util async mutex. And this now needs to be mutex new. And now what we do need is some sort of like wake up handle. What is this? Like wake up handle. And what is this guy going to do? So in futures, the way that these like async runtimes work is you have these like future signatures that look kind of whack. What every like async block is getting converted to is basically something that implements this, right? And this straightforward, right? This is like our promised version of ourselves saying like, we were not going to fucking move. Everything's in RAM. Everything stays in the same memory location. You can like use pointers, shit, whatever. This is also passed in. And what this guy is he's a context that his only purpose is to provide a way for you to wake me up. You tell me it is time to rerun the executor. It's like time to pull things again. And the idea is that like if everybody is busy, right? Everyone says I'm not ready. What we do in our executor, what do we call our async thing? Future, I think we called it. What we do is if we don't see anything to do, we actually like halt the CPU, and the only thing that will wake us back up is like a CPU interrupt. Right. So what we can do is we pass in our context here, and what we can do in this wake up handle is probably like we would probably take in that context, and we would have like two ends to it. Maybe we would have like a, sorry, thinking. So when we call wait for, we would generate this wake up handle. And when the other end writes to the table, he would tell the wake up handle that he's like, hey, you're fucking good to go. And so probably that's like in here. Probably we have like function write mac. We take in self. We take an IP. This has to be an async function because it locks this like async mutex. And the IP is this IP adder. And the MAC address is a MAC adder. And he takes in the IP adder by reference, MAC address. No, by value because he's going to write them in. But also these like copy pastes. There's like, I think that since this is like a U8 array, every time I passes by value, it's probably copying the whole array, which is no good. So we will use references there. And in this write mac function, what are we going to do? We're going to try to lock the table. So we're going to say self.table lock await. And then we're just going to table insert IP mac, right? Which I guess needs a, oh, we need to dereference these borrows. Sorry, we put in IP and mac like this. Cannot borrow tables mutable, so we just shove a mute on there. And then we're gonna say like, if let sum handle is equal to self wake up as ref or something, we'll say like handle awake, right? So this is our way of telling this guy when he's going to be waiting on the handle. He's just going to say like, oh, now I'm good to go. Seems reasonable. So what's going to be in this guy? We're probably going to need like the waker, right? Because when this guy calls him, he's going to call wake on him, and that's going to go into like the context here has like a waker, and this is the guy who's responsible for waking up the task queue. So presumably that's going to be in here. But these contexts are by reference, and that's a little odd. But I believe the waker implements clone. Yeah. So we can just shove a waker in here. Which means that we're going to have to use core task waker. So we'll just shove that in here, task waker. Okay. And the wake up handle. One sec. He's going to thinking. We have like a wake on here. And this is just going to call self waker wake. Easy. And now it's like, what is this future implementation going to look like? Because that's the important part here. So this is going to be a future implementation, not for the wake up handle itself, but for a reference to the wake up handle. Let me look at this future implementation thing again. This takes self by mutable reference. So that actually can't, we can't share the wake up side and the waker side. We actually have to split them up. So we can actually here, our wake up is only going to be waker. And what's going to happen is on this call to wait, we are going to store the waker. Probably. Sorry. Thinking. That seems reasonable. And then, what happens on this side. We're going to have somebody who's waiting, and he's actually going to hold a reference to the ARP table. And all he's going to do is he's going to say, I'm ready when I see the thing in there. So this is actually, that's very easy. So we can say ARP struct ARP ready future, and his implementation for ARP ready future is he's going to take in the mutex hash map thing, and all he will have to do is he'll check it. So the output is nothing, right? Because this is just a waiter. He's not actually trying to get a value of any type. Here, all he's going to have a reference to this guy. So this is going to be a reference like this, and he's going to be with a lifetime of A. And all he's going to do is he's going to self table. Shit, sorry, I have to handle some import shit. So core pin, and core task poll, and core task. Maybe it's task context as well. Yeah. So all he's going to do is, sorry, got to fix more errors before I keep talking, or I'm going to get distracted again. All he has to do is he's going to say, let guard is the mutex, so we'll say self.table.poll lock.poll poll unpin. God damn it. So here we're going to get a future to a mutex guard, right? This lock function is a async function that returns a mutex guard. So we'll just say, here's the guard. And if you fail to acquire the guard, then that means that we're not ready because we can't acquire the mutex. And so we'll say guard poll, and we'll pass in the context that we have been provided. And we'll say if let poll ready value, or we'll do a match statement here. That's easier. We'll say match this, right? And if we get poll ready, we just return, we like propagate that on. So we'll say guard is this. And otherwise, which I think is just poll pending, we'll just return poll pending. Okay. Now we have the guard, and we can say guard. This should be of type mutex guard hash map. So we can just say guard contains key, and that's going to be the IP that we're looking for. Which means that here we should just be able to say IP is a IP adder, and hopefully we can just share the lifetime here, share the love, and then here we just say we're ready if we contain the key. Yep. Otherwise, we return poll pending. And maybe we don't actually need to wake up the executor again here. We might not even have to stash this waker, because the concept that we're working with in our executor is that the only thing that can like cause something to progress from an external source is an interrupt, but this is like an internal source. So as long as our executor loop tries to run futures until until it gets a not ready, then we're good. So the question is if this like future select, if I try to combine these two futures, right? I try to combine the waker, the write side and the read side of this ARP table lookup. The question is, am I going to get a poll? Is like my future going to resolve, or is it going to return pending too early before it's actually not ready to continue? So we'll kind of keep that in mind. There's like a very good chance that this implementation will hang on this ARP table weight. And if that becomes a problem, then we'll deal with it there. Oops, did I accidentally delete something there that I didn't mean to? Yeah, I did. Okay, so now on the read side, all we should have to do is make our waiter. So we'll say like ARP ready future. And he takes in the IP is just passed in. And table is self.table. And we should just be able to await that. And once we've awaited that, then all we should have to do, we should be guaranteed at this point that the item is in our table, which means that unfortunately we've released the mutex here. So maybe the output here actually should be the IP. Or sorry, the MAC. And here, instead of saying ready this, we're going to say, what is it? Guard.get. And we just pass in self.ip. And then I think it's like some v goes to poll ready v. And none goes to poll pending. Nice, 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 nice. That's coming together clean. Okay. Yeah. So now all we have to do is return this. Thinking. Yeah, that seems fine. Okay. So now, we have this like outgoing stuff. And now we'll just have to hook in our receive loop to the same area. So I guess what we'll want to do is we're going to want to we're going to want to do this outgoing stuff, then sleep and wait for our receive stuff. So probably this like sleep future here that we're doing right here, we'll just call this something else, and we'll just do it at the end. So we'll say like let outgoing. Oh, we don't have to do let outgoing here. We can just drop the outgoing. At the end of outgoing, we'll put this stuff in here. Right, and we'll just say, wait, sleeping for 5 seconds to wait for incoming connections. And we no longer have to like name this. This is now a just a weighted thing in here. And here, instead of sleep fute, we'll say let outgoing is this pin shit. Like this. And then instead of waiting for the sleep future, we're going to wait for outgoing. Clean. This shouldn't be awaited. It should be like this. Clean. Okay, so now, theoretically, we should, in our receive loop, we should find that we get an ARP response somewhere. So what we should actually do is we should go into our like ARP handling shit. And here, we should, we'll promote this to a warn log, just so that we see it come up. And what I expect to see here is that we see a warning that says we like received an ARP reply, ignoring. Also, we get back that this like ARP lookup failed. So these are two like really good logs that indicate that everything is hooked up like semi-correctly, which is pretty sick. Okay. So now all we have to do is in this handle ARP frame, we take in our like ARP table. So we'll say like ARP table is we'll stick it at the end, fuck it. ARP table is an ARP table. On reply, we'll write it down, the reply in the ARP table. So I think we'll just say like ARP table, or ARP frame, I should say. Get, what does this guy have on him? I think that our ARP frame has all of the things we need on here to get it. It's sender protocol address and sender hardware address. So all we have to do here is say ARP frame dot sender hardware address. So we'll say let MAC is the ARP frame sender hardware address. try into dot expect. This is because we're working with a slice instead of an array type, and slices are like size things, and arrays are like compile time sized, and we're just basically asserting that we got those two things synced up. So we should say here arp MAC address, not the right size. And here we do the same thing, but the IP is not the hardware address, but the protocol address. And here instead we'll say arp IP address, not the right size. And then we can just say arp table insert or write MAC, and here we get the IP to the MAC address. And these should be references. Cool. So now we just have to propagate this like arp table down where it needs to be. So we'll say arp table here, which means that this handle packet needs an arp table, which means that here we need to pass in arp table, which means that our receive loop needs the arp table. So like we pass this in here, which means that we need to pass the arp table in here. Okay. So we're just missing an await on here. And let's see what we get. Holy shit. God, it feels so fucking good sometimes when you just like write a bunch of shit and it works the first time. God. Oh, that feels so good. So this should actually say figure out how to get the MAC. And we'll write that down here, and we'll say this took an hour. Good stuff, man. Yeah, thanks. It feels good. I love it when that happens. It's rare, but man, does it feel good. Now you should plug that monotonic down to the table as well. Yeah, I don't know. I like the idea of it being separate, just like conceptually. I do think that it would be nice to be able to call like sleep, just like in general, without passing in all this state, but it is also kind of nice for the state to all be like, to avoid like the static variableness of it all. I don't know. I mean only for entry expiration. Yeah, I get that. But like with futures, it's kind of fun. I like the idea that like the API doesn't have to support sleeping. Like that's not its job. Someone else can support the sleeping, right? It's kind of like ultimately flexible, which is kind of fun. But we'll see. Anyways, I'm happy with that for now. So here we've got our entry expiration thing going. We've resolved a MAC address, which means that we should just be able to start like pumping out some shit. So I guess the first thing that we need is we need a UDP request or UDP packet. Right. So for getting back into context. So the first thing that we were trying to do all stream is send a UDP packet to the host. And we spent a lot of time on like, where the fuck is the host? Who is his MAC address? How do we send him? And now we've got that. So now we can go back to generating a UDP packet that has the correct hardware addresses and stuff filled in, which means that the first thing that we need to do is we need to generate a UDP packet. So we'll say a UDP packet is net. There is no generator for this yet, but we've kind of got this pattern right now where we request a just bunch of bytes from these guys, and they are responsible for these like free functions. We call these like free functions with some parameters, and they're responsible for popping that back up as a bunch of bytes. And so what we would do here is we'd say like, my UDP packet is going to be generate UDP frame. Maybe UDP frame is a more correct term. I actually don't know what the correct terminology is regarding frame and packet, but I'm pretty sure I see frame on like stuff inside, and packet is like the box as a whole. So like a UDP frame will be inside one large packet or something, but I don't know. I'm just guessing based off what I've read. And in here, presumably there will be some sort of like params, but for now we'll just kind of like make this empty. Frame is more often Ethernet layer, packet is more often an IP layer. that sounds reasonable to me. I also saw within like the Ethernet thing though. I also saw like within an Ethernet packet. Wait, what the fuck? This isn't where I was reading before. Ethernet frame maybe is what I was looking at before. Like within an Ethernet packet, there's an Ethernet frame. So there's like layer 1 and 2 stuff going on. I don't know. Anyways, we will generate a UDP frame, and we'll assume that this is like a bunch of bytes. So we'll just type this now so that the Rust compiler, before this is generated, will figure out the right thing. Then, from the UDP frame, we'll inject that into an IPv4 frame. And so, again, we'll need a generate IPv4 frame. And then from there, we'll have something to shove into an Ethernet frame. So this will be net generate Ethernet frame. And here we have like, this is already built, so we have this thing stubbed out. And this is going to kind of like guide what we're going to do for the other guys. So delete these pubs, delete the stuff hanging off the end. And so here we would say like IPv4 frame goes here. The destination MAC is what we got. So this is MAC. The source MAC is going to be what we have in our network card. So that's this function here, which says like, hey, network card, what's your MAC address? And the ether type is going to be ether type IPv4. So there's no IPv4 ether type, so we just have to make one. And I think that that's here. IPv4 is this guy. Yeah, so the packet is in the Ethernet in the physical layer below. So unless you have a really low level NIC, you can always mostly ignore packets. Yeah, so I guess I should be using the word frame essentially everywhere. And I've got the word packet littered around my code base. So I've probably just kind of made like a naming faux pas in here, but that's okay. Maybe I'll fix that later. Maybe I won't. It's kind of fun to have my documented easy. Okay. So we have IPv4 ether type. Done. Then our IPv4 frame, we actually need to make that generator. So that'll sit down here with all the IPv4 shit. Which is somewhere. Parse IPv4. Here we go. Here's my IPv4 frame. And so I guess here is where I would stick this. I'd say like function, public function, generate IPv4. And this will take in some IPv4 params later, but for now, we'll just say that this returns a vector of U8. And we'll call this unimplemented for now. It's on, like, looking at, like, the way these APIs are sitting right now, this actually feels kind of shit, right? Because, like, what happens is each one of these guys, like, allocates a new bunch of bytes that we, like, copy into the other one as part of the payload. And that, like, sucks. Because it means that if we were sending, like, a large packet, we're actually just double copying for no fucking reason. So we'll just put that on the future thing here. Future, we'll say, like, the double, triple, quadruple copy for every packet construction. UDP, IPv4, Ethernet. But, I'll deal with that later. I think probably like you start the obvious thing that you would do there is you would like take a vector. You would inject instead of a reference to the payload. You could maybe inject the full payload itself. But then you get into like this kind of shitty state where your headers need to come like before the data, and so you might actually want to start looking at this like vector of vectors thing, or maybe some like linked list of vectors or something where you have like really cheap insertion of chunks of data, where you could have like header followed by payload followed by payload, and then like just you could still work backwards, right? Because the Ethernet frame you can't construct, or some parts you can't construct without knowing the length of the inner parts, but then you can at least have like cheap manipulation of those things. Probably a vector of vectors is actually probably pretty cheap, because you're probably only going to have like 3 or 4 layers of these things, and working with like 4 pointers in a vector should be like really cheap just to swap those around. But the problem for another day. We're getting distracted again. So in here we have generate IPv4. This should be generate IPv4 frame. And we just need to do the same thing with generate UDP frame, which I think is probably down here somewhere, yeah. This now needs to be called UDP frame, which means that everything should compile, actually. So we accidentally flagged these as the wrong types. Yeah, okay. So now let's just start looking at what we need to shove into these guys. So we'll look up UDP frame on Wikipedia and see if that just like gives me what I want. UDP, and his frame is simple. Source port, destination port. Why is this red? I assume because the source port doesn't fucking matter. The field identifies the center of port. When used, it should be assumed to be the port ready to reply if needed. If not used, it should be 0. If the source host is the client, if the source host is the client, that string of words is not registering well in my head. The port number is likely to be an ephemeral port. Reds are both optional. Yeah, that makes sense. If the source port is a host port server, the port number is likely to be a well-known port. So I guess for now, we will just not support anything except for dest port as an IPv4. Nope. That's not an address. This is a port. So we'll just call this a U16. Is that right? Yeah, 16 bits. And length. But instead of length, it should be payload. Right? And so I assume what happens here is the data's just sitting right after the header. I can just double check on the other side here. Or in Wireshark, look at this guy. But I don't have a dump here. So let's just look at the parsing code. I'm pretty sure it's right after. The Raggy is telling me that I'm correct, but I just want to double check. So here I just have data as end of header. Yeah, okay. And looking at this, length contains the header length. So here what we actually end up with is length equals header length plus payload len. And now the dest port we've got in here. And now we just allocate our shit. So we say we have a return thing and it's a vector. And he's got a capacity of this like provided length. We copy from slice, I think it's called. No, it's extend from slice. Yeah, here we go. First we have the source port. And so we're just going to say 0U16. Or I guess here we can just say like 016 is one way you could do this. Or you could say 0U16 2 BE bytes. And I'll probably do this because even though we're not actually encoding like a real number, it's nice to like have this in our head that we should be using like big endian encoding for everything on the network. Our destination port is just the same thing, but it's dest port to be bytes. I should actually double check this is big endian. I guess if it's not saying, it must be, and probably somewhere else I'm using BE bytes on the other side. So yeah, it's pretty sure. Fuck, where'd it go? Here, length. So we have extend from slice, length 2 BE bytes. This is actually kind of sketchy, doing it this way, right? Like this length being untyped is really scary, because if, as it's showing right here, it would have resolved a U size, and this would have just punched in like way too much fucking data, right? This would have punched in 32 bits instead of 16 bits for the length. So I'm glad I thought of that, and that's annoying. So we'll just say as U16 for both of these guys. Okay, and then the last thing we have is the checksum, which is also optional, maybe used for error checking. Nah. And all zeros. So we'll do the same thing here. So we'll just say checksum here. We'll put some comments. I don't really like doing it this way usually, but it's fine. Right, because usually you have like variables that you can use to name. And like, you know, you could just say like source port is 0u16 2 BE bytes. Do I like that better? Yeah, I like that for now. So let's pass in source port and const checksum goes 0u16 2 BE bytes. And here we just pass in checksum again. Oops, this needs to be like this. We need to provide types for these, which is like this. I found out recently, this like making these like arrays is like kind of annoying because you have to know the size of the array, but you can actually just make these like slices instead and do this, which is kind of fun, I think. And then just get rid of the ends here, and then the compiler just like figures out everything you care about. Very nice. Okay. So now we go back to main. You won't be able to skip checksum for IPv6. Yeah, but our operating system was written before 1995. IPv6 didn't have exist. We had no choice. We didn't know. So destination port, I guess for now we'll just hard code as 6000. 6000 or 6001? Which one was it? We're listening on 6000. Rust going back in time, Hackerman vibes. Perfect. And here we'll just put a byte string of like, hello from inside the OS. Hopefully that's not too long. Because I'm sure that if my my packet goes over what was like MTU is like 1536 or something. 1518 is with an MTU of 1500. Yeah, this is what I see a lot. I'm pretty sure that if I ever go over that, we're just gonna do some dumb shit. Because I've never tried to split anything anywhere. But for now, we will continue just keeping that in mind. And then from our IPv4 frame, what are we gonna do? Of course I could have jumbos. Oh, that's right, I have seen that. Jumbo MTU. Jumbo frames. Ooh, wow. Does everyone have these? Yeah, IE 8023. Mini gigabit Ethernet switches. Yeah, so I guess what happens, when we connect Ethernet to the switch in our PC, you have that like, there's like that like Ethernet negotiation protocol. I can't remember what it is, but you can like look at it with ETHTool, and you can like, probably part of the negotiation is the maximum frame size, and new switches tell each other like, hey, don't fucking worry about it. You can give me anything up to 9K. Probably. Neat. Neat. Okay. IPv4 frame. What's going in here? Probably the destination MAC and size or something. We can just look it up. IPv4. Okay. Version, I think this has to be fixed to 4. This is the size times 5 or something. Don't know. Packet size in bytes. It's crazy that I've managed to get this far without looking at this. In fact, I've probably fucked something up by not looking at this. Because there's like header length here and total length. Yeah, okay. So this will just be probably the size of the Ethernet frame, the whole thing. 20 bytes, header without data. Okay, so anything in IPv4, including the header. Identification, what is this guy? Field is an identification field and probably used primarily for uniquely identify the group of fragments of a single IP datagram. Some work has been suggested using the ID field for other purposes. So do I just punch in? Okay, what we'll do is we'll start by turning back on our listener, and we'll just make a network dump that where we are sending shit. Fuck, not implemented. Right, because we're compiling and this stuff doesn't run. Fuck, okay. We'll just comment this out for a second. Cargo run and netcat fuck test. Okay, that should be enough so that our Wireshark will now have an example of an IPv4 packet frame. Sorry, words are hard. Okay, so in here, what does he say? He says the identification, he just writes to 0. Cool. He's got the protocol. Okay. I think everything in here is probably pretty easy. So what's DSCP and ECN? Are those shown here? Pull this over a little bit. So this stuff we understand. Version, which means that this is DS. What is it called? DSCP. Originally defined as a type of service. Blah blah blah. An example is voice over IP. So we'll just copy this, which is 0. What the fuck is ECN? Oh, ECN is embedded in here, so we'll just copy 0 in there as well. It's all flow optimization. That makes sense. So, like, if you mark your thing as a VoIP packet, you might get, like, lower latency. Yeah, QoS mechanisms, right. So I've seen this on servers before where, like, or on routers before, where you can say that you want lower latency on VoIP packets and stuff. So I guess that's what they do is, like, the Ethernet, the IPv4 frame goes like, hey, I promise I'm VoIP. And then your router goes like, oh, quick, shove that to the front of the queue or something. Yeah, and ECN is congestion notification, aka please slow down. Yeah, it makes sense. Cool. So basically, I just don't give a shit for this case. It's easy. This is 0. What about flags? A 3-bit field follows and is used to control or identify fragments. Don't fragment, more fragment. So I'll probably use don't fragment, I assume. Unless maybe fragments are reconstructed on the other side fairly easily. What did my incoming thing say? Flags was 0, not set. So he just said 0. I guess I'll just say 0. Although, I guess this guy's saying, I haven't set don't fragment. Like, the Wireshark capture I have hasn't set don't fragment, but I guess theoretically somebody could have fragmented and it would have broke my OS. Unless... I was going to say unless the Ethernet card handles it, but that doesn't make sense because it's the IPv4 layer, which is completely independent. I guess don't fragment, sending it from my side probably doesn't matter. That's just my guess. Right? Like, if I send it to someone else, I'm like, routers, fragment the fuck all you want, because I'm not talking to me. I'm talking to someone who knows some nicks can do the work. Yeah, that makes sense too. Right? I can imagine that those, like, hardcore switches, they'd want to start, like, in hardware getting into the nitty-gritty details because you can get some speed optimizations out of that, probably. Okay, anyways, getting distracted again. I'll just use 0 because I don't care. Fragment offset specifies the offset of a particular fragment relative to the beginning, but since I'm not fragmenting, this will probably also just be 0. And we see that in the Wireshark capture for the things we're sending right now. Time to live. Limits a datagram's lifetime. So this is probably when I am going onto, like, I'm like going through routers. Every router is probably like storing the packet for a little bit. And this is like how long I want them to store it for, and they can probably just fucking ignore me. Let's see what this actually says. When the TTL is 0, the router discards the packet and typically sends an ICP time exceeded message to the sender. Time intervals, less than 1 second are rounded up to 1. And this is used as like a hop count. Sure. I guess I'm not really understanding why they need to store it ever. But, like, I would think that the router just, like, gets the packet and just, like, immediately, like, barfs it onto the network in the right direction, but I must be missing something. It's a bit of a junky value these days. Interesting. Protocol, this I know has to be UDP, header checksum. Do I actually have to calculate this? 16-bit IPv4 header checksum fields used for error checking of the header. When a packet arrives at the router calculates the checksum of the header and compares it to the checksum field. If the values do not match, the router discards the packet. Fuck. Both UDP and TCP have separate checksums that apply to their data. Fuck. When the packet arrives at a router, the router decreases the TTL. Oh, oops. Wait, why? How is this related? When a packet arrives at the header, that router... Oh. When a packet arrives... So the router also does some new checksum calculation. Okay. Checksum is 15-bit one complement of the one complement of sum of all the 16-bit words in the header. Oh, that's pretty easy. Assuming that one's complement sum is easy. I don't actually know what that is. Ones complement sum. Ones complement. Oh my god. Here, Wikipedia. Ones complement value. So here it's just unsigned value 128 goes to negative 127. How is it different than 2's complement? How is this different? So 128 goes to negative 128. So is it just 2's complement plus 1? Yeah, it's just 1. Oh, I see. Yeah. It's just the they don't have double zero. Is the only difference. Does that make all of the does all the math still just work out there? It must, otherwise it doesn't make sense. Okay, so probably I just thinking. So ones complement sum, it said, was the checksum. Did I lose it? IPv4 checksum. Ones complement sum of all 16-bit words in the header. So I guess I just add it. Since everything's unsigned, why even talk about one's complement here? I would think that if I'm just working with unsigned and I add everything together, it would just work out. So maybe there's like an intricacy there that I'm not thinking about. So if I do like 0001 plus -1, this would turn into 0000, which would turn into 0. Oh, but that's 2's complement. Fuck. So here I would do 0001 plus 1111, and this would turn into 0, which would be 0. So that's the problem here, is that the math, if I just do unsigned, if I just use these as additions, then it doesn't work. Am I reading that right? Yeah, the negative values are 1 off. You can probably, yeah, something like that. Oh, that's annoying. So is there like a way to do one's complement in C easy? I'm saying C because I don't want like some Rust library. I want somebody to just give me the code. That's usually how they do it. We do manual fix up every time. These are slow. One's complement using bitwise not. Okay, sure. So this is just bitwise not. And one's complement sum in C. Oh, does somebody answer this? Here's the code for UDP checksum. Where is he doing the one's complement? One's complement add. Where's his one's complement add? Oh, he just doesn't have. He just hasn't implemented it. C one's complement and try uint32 sum equals n, sum equals k if sum and otherwise sum plus 1. If this is sure, if this is positive, then we add it. Oh, I see. Basics. Adding 2 values is straightforward. Simply align the values on the least significant bit and add, propagating any carry to the bit 1 position. If the carry exceeds passing the word, it'll have to be wrapped around and end around carry. When this occurs, the bit must be added back to the rightmost bit. I see. So I just have to check for overflow. And if we overflow, then add 1 again. This is the one when we optimized in WireGuard relatively recently. Interesting. Why? Come on, man. There we go. Yes, they say. They just do a bunch of manual adds here. So why is there no wraparound concern here? Are we just assuming that we can't? Mask and shift is equivalent. Oh. I see. So shifting by 16 Oh, on a 64. Checksum no fold. So this is probably the interesting part here. So n is the length of the thing. Yeah, I see. And I plus equals 2. No, I don't see. I'm lying. So the oh, I see. So you're packing all of the checksum. You're packing several things into a UN64 and then shifting as its like mechanism for. Yeah, okay, that makes sense. I do want a more primitive version though. I want to do the stupid thing first until I have a problem. So I assume that there's like check for overflow in Rust. Add check overflow or something. So they have checked add, and this guy will return an option. He will reject it. I don't really want him to reject it though. I want him to like do a wrapping add and tell me if he wrapped. Right? Because that's all I have to deal with. So wrapping add. Ugh. Overflowing add? What's this do? This is what I want. Returns a tuple of addition along with the boolean indicating whether or not the arithmetic overflow would occur. Okay, so that's pretty easy. So we can just call overflowing add. If we see the overflow, add 1. Sure. Sure, that works for me. What's the difference between this and carrying add? Self plus RHS plus... Oh, I see. Okay, sure. Okay. That's all I wanted. Okay, so I think we have all the pieces we need. That took a while, but we got what we want. So the version I think is just hard-coded to 4 because I'm IPv4. Yep. So let's just start smacking these things in. So we don't need this open anymore. Go away. We can open this, and we generate a UDP frame, and now we just have to generate an IPv4 frame. And the first thing that we're going to have to do is we're going to like make a return variable is vec new. We'll see if we can find a good capacity later. We return ret, and the first thing we do is we punch in that header and IHL. So we're not going to have any options because we don't know what those are, so we can't. Which means that the IHL is 0. And we also noticed last time on the decoding side of this that the bit numbers are actually swapped. So on our parsing here, we had to use bits 0, like a 0 shift and the bottom 4 bits to get the IHL, but this should be the top 4 bits. So I think we just like swap everything here. We just pretend 0's on the right. Because I'm assuming that's because the network card is handling some shit in there for us. Okay, so what's the play here? We have IHL is going to be 20. Version is going to be 4. Which means that we have 20 in hex is just... what is that? 16 plus 4. So 1 4, I guess. So we'll have push 0x 1 4. No, that doesn't make sense. This should fit in 4 bits. Oh, because it's times 5. The IHL is like times 5 or times 4 or something. This is the number of 32-bit words, so it's times 4. So we just have this is 1, 2, 3, 4, 5. This should just be 5. And the version should be 4. Okay. So this is version plus IHL. Now we have DSCP and ECN, which we said are going to be 0. DSCP and ECN. Total length is a U16 big endian order. So that's just the payload size plus the header size, and the header size is going to be 20. So we'll just say const Header size is a U16 20. Is that right? 20 bytes. And so the length here is the header size plus the payload size. So here we're gonna have to take in a payload of U8 slice, and this is gonna be extend from slice. We're gonna take in the header size plus payload len as U16. That's sketchy. Fix me usize U16 truncation. We'll handle that later though. 2 BE bytes. Okay. So that's the length. The identification, I think we just said could be 0. So that's 0 U16, 2 BE bytes, and that's identification. Did we get the size right here? We lost the header. We lost it. We lost it. Header. Identification, so that is a U16. Flags. I think we just said that all of this is going to be 0 as well because the flags relate to fragmenting, and the fragmenting is offset 0, so we're just going to say 0 here again. So we'll say this is flags plus fragment offset. TTL is going to be 64 because we saw that in Wireshark. Wireshark incoming packet. Protocol is going to be UDP. So I guess here we also have to pass in the protocol. So we'll do ret push protocol as U8. Non-primitive cast. No. Ugh. Because it might be unknown. So we'll just make an impl for this, I guess. We'll implement a core convert from for IPv4 protocol. And this is actually from IPv4 protocol for U8. And we slam an implementation in there. T should be IPv4 protocol. And we just say match self UDP goes to 11, which I guess we can say IPv4 protocol. I wonder if we can do like V goes to V as U8 and then only handle unknown. I wonder if that'll work. That'd be cool. Self value. This should be value, not self. Consider using from trait instead. But does it compile? No, it doesn't like that. Fuck. So I guess I actually just have to say, like manually, it's like UDP goes to IPv4 protocol UDP as U8. Does that work? No. Fuck. So just because I've like punched in this like unknown thing, I have to like duplicate all these that's number. That blows. That blows. But that's okay. We'll deal with that for now. Or live with that for now. So that means that here we say, instead of protocol as, we say protocol into. And now we have the header checksum. So the checksum is going to be, what did he say? 1's complement of, I think he said in U16 space. And by he, I mean Wikipedia. 16-bit IPv4 header checksum is, both UDP and UTP have different checksums. So here, we're gonna have to match the protocol. And lucky for us, we have everything else is unimplemented. Fuck it, we crashed the kernel. I don't care. And maybe we'll say checksum for protocol not implemented. like this. And for UDP, oh, good eye. He is saying you see UDP and TCP have their own checksums, but the IPv4 one is the same. Let's double check that. When a packet arrives at the router, blah, 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 have separate checksums. I was reading separate as in the field here is going to be different. But you're saying that since they're in their own pack, like, you're saying that they're internal. That makes sense. Errors in the data field must be handled by, yeah, okay. Sure. I would allow, I'd accept that. And if you're wrong, it'll be really obvious really quick when we try it. So here we have to like calculate checksum for ret. And this is calculate IPv4 checksum for ret. And then we just say ret push, or this is going to be extend from slice because it's U16. And it's going to be checksum 2 BE bytes. And so now we just have to implement this guy. So this is going to be a function, and he's going to take in a data that's a U8 slice, and he's going to return a U16. And what's going to happen in here? We're going to iterate over the data as U16 point values. I wonder if that fucks anything up. Thinking. It actually is important for wraparound. But do we want to do like big endian or little endian logic? Probably we want to convert all of these things back to little endian so that we can just get like free math and then convert it back to big endian, which is a little bit of a pain in the ass, but that's fine. And, you know, we know for sure that there's a faster way to do it. But we're not going to worry about it. So, I guess we're going to say, we're going to chunk the data by 2s. So I guess first we're going to make sure that the data is a multiple of 2. It should always be. So we're going to say this. We're going to say that if the data len mod 2 is not 0, there's a bug in here. Now we can iterate over the data in chunks of 2. So we'll say for A, B, or it's probably something like slice in data.chunks. It returns the iterator over chunk size elements of the slice at a time, starting at the beginning of the slice. The chunks are slices that do not overlap. Perfect. So then we have our checksum. It starts at 0. It's going to be mutable. And then we're going to return the checksum at the end, obviously. Right? And now all I have to do is we say, like, we try to convert the slice back into an array of 2. And we know that will work because that's like a compile time thing. And then we try to convert those into a U16. So we say U16 from BE bytes. Right? And this is going to be slice. Dot try into dot expect slice should be 2 bytes. Okay, so we have this value, and we're going to do a ones complement add, which means we do a checksum overflowing add checksum. This should be a checksum, not a chucksum. My name is not Chuck. Okay, checksum overflowing add. And this is going to be val. And so this is going to be checksum equals this and, no, sorry. So we're going to say overflow result is this. Checksum is equal to overflow res 0. And if overflow res 1, i.e. we overflowed, then we just add again. Okay, so, and really this should be called like ones complement add or something, but that's okay. So we'll just call this a ones complement add, maybe should be factored out. Okay, Am I spelling complement or complement? Complement. Why not destructure the tuple out of interest? I didn't think that you could destructure the tuple into like a new value and an old value, right? I thought that I couldn't do like checksum overflow res, but like if I did let checksum overflow res is equal to this, or sorry, yeah, I guess this would be fine. This would like create a new checksum variable, right? He's saying like, hey, that's an immutable variable. And so I think I have to do like maybe this, but then overflow res doesn't work. But I think that I maybe do this. If I overflow. Yeah, okay. Good call. I thought that I could I didn't think that this syntax existed 2 seconds ago, so that's kind of cool. We learned something. Overflow res. There we go. Nice. Very nice, very nice, very nice, very nice. Okay. So then we just calculate the checksum of ret and we return it. Bing, bang, boom. And I guess this is done. So now we just have to shove the payload in here. So ret extend from slice payload. And that means that in main, we have a UDP frame as the payload and protocol UDP. We have to borrow this frame. And the Ethernet frame is done. And we can write that. Ethernet frame. Wow. Okay. First time looking plausible. Nah, I don't believe in it. UDP is the same as the variance. Blah, blah, blah. So this is a net RS 1554. What's it bitching about? Oh, I forgot to write this in front of it. Not implemented. What's not implemented? God damn it. Okay. So now we can look at the Wireshark dump again and see if we got anything interesting. Bad UDP length. God, Wireshark's so fucking sick. So sick. This would have taken me so long to debug without it. Okay, so what doesn't he like in here? UDP data programmable. Source port 0, des port 0, length 0. So something in here is just like totally fucked. Okay, so let's look at this. We have a generate UDP frame. We create a return with a vector. We punch a bunch of shit into this ret, but we don't punch the payload in. That would do it. Let's try again. And let's see what Wireshark says. Bad UDP length is way longer than the IP payload length. Okay. So we do have hello from inside the OS is in here. It's looking decent. Okay, so what does it say? UDP length is greater than IP payload length. So let's look at both these guys. So the UDP length, yeah, you're right. This being like 28448 is fucked. You're right. You are right. So, oh, this is bogus. Payload length 30. So does this say 28? The fact that it thinks that the length is here in like the middle of my string is like an indication that we really fucked something up here, right? Because the UDP payload, we probably just put the wrong thing in here. generate UDP frame. We put the UDP frame in the IPv4 frame. Did I forget to write my UDP header? I don't really see how that would be possible, right? Like, I'm generating the UDP frame here. Here I have this like return thing. I extend it with all of my shit with the payload at the end and return the ret. So that gives me a thought that like the IPv4 frame is probably broken, right? Like probably at the end of the IPv4 frame, right? Like we see this is just fucked, right? Like destination address 0.32.0.0. So we've made a mistake in here somewhere. So let's try to like count up the size here before we add in the payload. So we'll just print line IPv4 length is IPv4.len. And, oops, not IPv4, ret.len, sorry. And we run it again. And here we said IPv4 length is 12. So that's obviously wrong. God, I'm gonna be so mad if this isn't like a U8 vector. Okay, it is. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, yeah. There was more stuff in the checksum after the checksum. Yeah, that would do it. Okay, so you have source IP is an IP adder. Dest IP is an IP adder. And we say ret extend from slice source IP and dest IP. Wait, am I high? How could you calculate a checksum without the rest of it in there? Does it just not include that part? It includes the checksum for the head of the header and compares it to the head checksum fields. Like, you can't have the checksum in the checksum. The checksum field is 0. Oh, so I start with a checksum of 0, then compute the checksum after, and then inject it? Yeah. Alright. Oh, for the purpose of computing the checksum, the value of the checksum is 0. If I had read 2 sentences farther, I would have got there by myself. But, can't do that. Okay. So, here, I guess we'll say checksum location is going to be len at this point. We're going to put in 0u16 to be bytes, and then at the checksum location, we're going to say ret checksum loc to checksum loc plus 2. We're going to copy this from checksum.2be bytes. And we need to borrow in here. And now we need to punch these guys in. So here we just need source IP is my IP. And the destination IP is the, I've written that somewhere, remote IP. Okay. Right, so that IP adder is like a new type that doesn't exist yet. So in net, we'll just use crate IP adder. All right. And is there like a refresh button? Ugh, can't click it. Fuck. Hey. Okay. So this is a UDP packet. And now the question is, what do I have to do to see it printed on the outside? Because from Wireshark's perspective, this is working fine. So let's double check my qemu run command. So we have host forward and guest forward. The guest forward is things from this are going to this car dev. Oh. We need to listen on 6001. And maybe that'll just work. Carter run. Come on, baby. No. No dice. No dice. Did I just not put the source of the ports anywhere? I need to be writing to port 6000. Did I write that in there? Main. Main. UDP frame. I did write 6000 in here. And in Wireshark, I do see that the destination port should be 6000, I think. Let's just double check that. Des port 6000, link 32, source port 0, checksum 0. UDP payload data is hello from inside the US. Yeah, so I don't really see anything. Source address 10.02.15, dest 10.02.1. Let's double check that my QEMU wrapper has 10.02.1 as the destination. So if you want Wireshark to validate your checksum, you might need to explicitly turn on the checksum validation. Oh yeah, I guess it could just be like totally fucked. Can I just turn that on? Protocol preferences. I saw somewhere. I have seen that option. Was it here? Protocol preferences, UDP. Validate the checksum if possible. Oops, I want the IPv4 one. Protocol preferences. Validate checksum if possible. Hey, nice. Maybe caused by IP checksum offload. Should be 62AA. Dude, that's so far off from what I got. What the fuck? Wow, I got fucked. Okay, header checksum status. Bad. Okay, so we just go back. Okay. So here, let's just double check that we punched in the right thing. So here, if we print line the checksum and we print it in hex, let's just make sure that what we see here is the same thing that Wireshark is telling us it found. So it found 9D55, and that is what we got into Wireshark. So we're inserting it in the right place in the packet, and it's just we fucking suck at calculating this. So let's double check that we got this right. Blah, blah. When a packet arrives, the route calculate checksum of header, blah, blah, blah. Computation. The checksum field is a 16-bit ones complement of the ones complement sum. Oh, fuck off. Okay, let's try that again. 62AA. And 62AA correct. Okay. Sick. Sick. So, protocol preferences, IPv4, we have got a good checksum. We're sending to the right place, both in Ethernet. Let's just double check here. So my destination is in fact 5255.0A.0.0.201. So our destination address is correct at the Ethernet level. I guess we could maybe double check the FCS. So let's unverified still. Protocol preferences, Ethernet. Validate the Ethernet checksum if available. So this is fucked again. Fuck off. It's reversed. Generate Ethernet frame. So I guess probably just all of these have been fucking broken. And I guess internally QEMU's allowing it, but maybe however QEMU's piping that into my host is not. So this should just be 2 LE bytes. And we'll just put a note in here that the checksum for some reason backwards. I guess we should fix me because we don't understand this at all. Okay. Open it again. And so here the FCS is good. The checksum is good. The data is good. So now the question is, Why don't we see anything? Everyone in Wireshark so far seems to be happy. Natting updates are lightweight and don't validate because speed. That makes sense. QEMU wrapper. So I guess there's like a very real chance that what we've done here isn't right, or something's not working as we expect. So let's look at guest forward, or QEMU, and look at the guest forward again. Earlier we deleted this 127001 somewhere. Somewhere there was like a, oh, in the car dev, I think we deleted it. So here we could try putting host equals 127.0.0.1 in here again and see if that helps us. We have port 6001, which I don't know if that's like the sender or the receiver. And there's also a good chance that we're clobbering each other's ports. That's also a very real option. So let's delete that stuff. Run this. Address already in use. Oh, okay. So that's interesting. Address already in use. So here it's fine, but if we spin this up, now we can't listen on that port. Oopsies. So that means that QEMU is binding to that port. Is 6000 the one I want? I would have thought no, but maybe? Where guest forward, I think, is inbound. I thought host forward was inbound. Because what I was doing before, to get stuff in, I was using this host forward command, binding, sending stuff to localhost 6001, and inside, I should be getting 6000. I actually haven't double checked that, so let's double check this real quick. Right, so if I go in here and I start like spamming shit, hold on. Am I sending to, oh, oops, this is nc.l. Oops, nc-u. So if I start, what the fuck? Test. Why is this not working? This was working before. Hold on. nc-u just needs to be 127.0.0.1 or something. Test. What the fuck? Is it 6001? Localhost 6001. Sorry. Cargo run. So if I start spamming shit, what we should see is in Wireshark, we should see it forwarding to port 6000 on my machine. Source port something ephemeral, destination port 6000, and those are being logged in my VM, and that's from the host forward. So I'm like binding a port on host and forwarding to UDP on guest. And so I thought that guest forward should just go the opposite direction, right? We should go from my inside. It reroutes things sent to address 10021, port 6000, and that should go into this character dev. And this character dev is this. And I wonder if I can just like maybe temporarily make my character dev like stdio or something, and maybe we'll see something there. I'm missing a UDP on the guest forward spec. You would think so, but the guest forward spec only allows TCP, and I was just like copy pasting from this link here. And this guy was saying like the way it works is you forward from a network guest forward to a character device, and this character device then should go to UDP of the host. Right, this is what this guy says. At this configuration, any guest UDP datagram sent to 10.2.0.18000, so that's this, which is what I should be doing inside, is forwarded as a datagram to 127.0.0.1.800. But then I don't understand why I can't netcat listen on that port if that's what this is supposed to do. So, there's also a good chance that this is just like some guy on the internet and I didn't understand it correctly. But let's look at this character stuff again. And maybe, since it's forwarding to it, you didn't leak a netcat, did you? That's a good question. I don't see any netcats running. Let's see if we can just get this guy on stdio, right? Like, car dev. Like, if I just paste this shit in here, do I just like get my stuff on std out? Serial STDIO can't be used by multiple devices. Okay, so let's just for now, we'll disable serial. And we don't get anything there either, right? I would have hoped that if I say forward everything to this character device, and that character device will just log to stdio. I would think that works, but I guess not. So I still don't understand why when I do cargo run here and I try to netcat listen, I think it's -l -u 127.0.0.1 6001. It works here, but if I try to listen here, it's address already in use. I'm so confused about that. Oh, wait, why does it say malformed packet? Wait, well, hold on. Does it only says that on the outgoing ones. Interesting. Okay. Oh, there's probably some like port conflicts going on here. Let's just take out this 6001. And we're going to make this 6002. I am an idiot. There we go. Okay, so we'll try that again. So now we don't have this like port conflict shit, but we still do have it not correctly making it all the way out. But we're closer. So again, we just refresh this Wireshark shit. And there's something wrong with like how this pipe. I'm like very, very confident at this point that our Ethernet frame and our IPv frame and our UDP frame are all doing something sane, and I'm like 95% sure that I've fucked something up in terms of piping from the guest to the host. And so I think I'm going to call it there. I think I'm like really happy with where we got, even though it's not currently working. And I'll do like some like offline testing. And if it doesn't work, then on the next stream, we can try looking through what we've missed some more. But I'm fairly certain that I'm just going to find some stupid fucking option that I didn't turn on. So thanks for watching. This stream was pretty fun. We managed to get like, what did we implement? Dump looks correct, so personally I'd just use VMNet or VNX. Yeah, I've been trying to avoid like doing like Mac VTAP and shit as well, because it's like more configuration, but I think it's gonna end up being less complex overall. So what did we do today? We got ARP requests working. We ended up with having this like async mechanism of where is this? Where we said ARP table. So we had this ARP table that has this like async function that will wait for a MAC to be written to it. So we got like the ARP request and ARP response hooked up correctly. We have like these like concurrent reader and writer. The writer says like, hey, who has this IP? And the reader, like, he gets it and he like sends it back to the writer. Thread, we'll call it. Thread's a little bit wrong because it's all async. So that was pretty cool. And then we got like these like Ethernet and IPv4 and UDP frames generated to the point where Wireshark is claiming they're correct. But we have not yet managed to see those effects on our host. But yeah, pretty good stream. Thanks for watching. If you like what you saw, I'm streaming most days at like 2 Pacific time. And if you missed the stream, you can always catch me on YouTube. The YouTube's linked in the Twitch description. And if you're watching on YouTube, if you want to catch me live, that's on linked in the description as well. So thanks for watching. Catch you on the next one. Bye.